is my Lab 4 report. Here's a quick overview of what I'm about to cover, starting with the introduction. First, the purpose of the lab is to observe the motion of an object attached to a spring as it oscillates, then analyze that object's motion in Tracker to find the object position versus time data, then utilize that data extracted from Tracker to build a computational model to accurately predict the position data in the specified time interval and change of energy of the system, and lastly, compare the observed versus predicted motion data on a graph. So some of the fundamental physics principles utilized is first momentum principle, which is F net equal to change in momentum over change in time. We also have gravitational force near Earth, where the magnitude is equal to mg, and then the spring force magnitude is equal to the spring constant times the stretch of the spring. And lastly, we have net force, which is just the vector sum of all the forces acting on the system. And because both of these forces are acting in opposite directions, we know that the addition of these forces equals 0. We also have the velocity update formula, where we can predict a final velocity if we have the initial velocity, net force, mass, and change in time. And same goes for the position update formula if we have initial position, average velocity, in this case, by final velocity and change in time. And lastly, we have the energy principle, where delta E is equal to the work on the system plus the heat change of the system. In this case, that's 0. And it's also equal to the changes of energies in the system. So in this case, it would be kinetic energy, gravitational potential energy near Earth, and spring potential energy all equal to 0, and formulas below. So a quick model description is that I developed the model in GlowScript and applied Newton's second law by utilizing the velocity and position update formulas to compute predicted position at each time step and utilize the energy equations to find the change of each type of energy and total energy of the system. Quick overview of results is that the results were relatively precise and accurate in predicting the system's position and change in energy between the observed and predicted data. So methodology, I first observed the motion of the mass attached to a spring, where the system was the mass, spring, and Earth, and there were no surroundings. And then I utilized the point mass feature in Tracker to record the object's position in the Y and X direction at each time step. So the initial conditions are listed below for the mass, the initial position, initial velocity, and observation start time. So now moving into the model encoding, we first need to look at the system properties and initial conditions. So we first include the mass of the object, the initial position and velocity, and the observation start time and time step. Then we look at the interaction constants, spring, and other energies, where we first include G, which is the gravitational constant near Earth, the spring constant, the relaxed length of the spring, the current spring length, L hat of spring, and stretch of spring, and lastly, calculating the different types of energies involved in the system and total energy. Next, we go to the calculation loop, where we first define initial energies, then calculate the gravitational and spring force on the system and add those together to get the net force on the system. Then we use that to update velocity and position. Then we also have to update the spring length, stretch, and L hat. And lastly, calculate energy changes to each energy involved in the system, as well as total energy. And as you can see here, this is the coding output. So on the left is the 3D motion representation of the spring and the object. And we also have the change in energy graph on the right. Next, we also have the X and Y position versus time graph. As you can see here, they are relatively similar between the model and experimental data. So quickly going into results and discussion, we have the comparison between the observed and model data. As seen in the graphs to the right, we see both X and Y positions of the system is very similar to that of actually observed, meaning our model accurately predicts the motion of an oscillating object attached to a spring. So some potential sources of error could include point mass measurements could have been more precise, and rounding and certain calculations of the spring constant and relaxed length of the spring could have contributed to the difference between the data. And lastly, the conclusion includes the what if, what does it mean questions. And we do see that the energy principle is satisfied because This can be proven in the change in energy versus time graph because change in total energy should be 0 for each time step, meaning this is satisfied since there's no work or heat change of the system. Therefore, change in energy of the system should always remain 0, and you can see here in the orange line it does. Lastly, we see that there is a slight difference between estimating the oscillation period using X position versus Y position data. And even though they're only slightly different, this would affect our calculation